Hello. This time we're going to go over the matrix representation of a linear transformation uh, in a more general setting. So let T be a linear transformation from vector spaces U and V with respective order bases B, provided just like that, and C, just as indicated there. Well, a few things that we need to say is the following. A note that any vector x in U is uniquely represented by the following decomposition. X being equal to, let's say, alpha 1 U1 plus alpha 2 U2 all the way up to alpha n Un. What we're saying here is that, well, since B is a basis, and is a basis for U, and X is an element of U, we can find a linear combination, a unique linear combination, satisfying this equation. So, there's another way of saying this. This also indicates that X is given by the coordinate vector column vector alpha 1, alpha 2, alpha n. So it's a column vector with n entries, where each of the coordinates, as you can see, corresponds to the decomposition given in that basis. Well, what we want to do is extract ideas and relations on the actual transformation. Let's see what happens when we let t act on that vector x. So t of x, right, now may be represented as t of alpha 1 u1 plus alpha 2 u2 plus blah 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 plus alpha n un. But recall that t is a linear transformation, so it preserves addition of vectors and scalar multiplication, so we may just write it in this fashion. Alpha 1 t of u1 plus alpha 2 t of u2 plus, and then we continue in this fashion until we decompose it like this. Alpha n t of un. Okay, and this is not a surprise. What we have here is that a linear transformation is completely determined by its action on a basis. So what we're going to look is at what happens with these particular vectors, right, that we have here. Well, let's do it. Let us see the action of t on uj for j running from 1 up to n. Well, once again, t is a linear transformation, and t of u of j now may be decomposed in the following way, as I'm going to write it a1j of v1 plus a2j v2 plus blah 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 amj of vm. Why this decomposition? Well, because the vector that we have here is in v, and, well, v1, v2 up to vn forms an order basis for v. So it admits this decomposition. In other words, I'm going to use the same wording that I had before. This is to say that Tuj is given by the coordinate vector A1j, A2j, blah, 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 mmj in the basis C. Okay, now what we're going to do is see the full action. And to do that, well, we just incorporate all the data. Then T of x now may be written as alpha 1 times, well, A1, 1, V1, plus A2, 1, V2, plus blah, 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 AM1, VM, right? That corresponds, as you can see, to T of U1. Now, to save some space, I'll just continue, right? And I'll add them. So I have alpha n times, well, A1n V1 plus blah, 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 blah. I'm saving a little bit of space here. AMN VM. Of course, this is representing here T of UN, right? Okay, now let's manipulate this a little bit to obtain the following. We can write it as alpha 1 A11 plus blah, 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 alpha n A1n times V1. What I want to do is to obtain the coordinates of T of x in the basis determined, the basis given by C. So I'll continue in this fashion. So plus blah, 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 blah. Then I say alpha 1 n. I'm sorry, not alpha 1 n, but directly just like this. Alpha 1 AM1 plus, well, AMN with alpha n times VM. Well, but now what I'm going to do is indicate this as a dot product. The dot product of what and what? Well, it's going to be A11, A1n, so this row vector times this column vector, alpha 1 up to alpha n, of course, times V1, and then all the way up to AM1, blah, 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 AMN times alpha 1 with alpha n, okay, times Vn. So what is that we're observing here? We see that for I ranging from 1 up to m, the ith coordinate in C, of course, of T of x is given by this, the following expression. A I1 alpha 1 plus A I2 alpha 2 plus blah, 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 AIN alpha n, which is the ith entry of the following matrix. Let me just draw it over here. Of the column vector, of course, seen as a matrix, A11 all the way up to A1n. Then we traverse in this direction, AM1. We traverse in this direction, AMN. We construct a matrix times a column vector alpha 1, alpha n. And I think with this we're done, because what we have here is, as you can see, an M by N matrix that allows us to transform or to apply, to be more precise, to apply T as a matrix product, as if we think of this matrix transforming the coordinates in B into coordinates in C, incorporating the linear transformation. So, what is how is it that we can summarize it? This M by N matrix is a representation of T from basis B to basis C. And well, if it happens that T is the identity, then we say that this matrix is the change of basis matrix. But for that, there's an example that is coming up.